Okay. So hello. I will, at your request, I shall start with sets, infinite sets, and countable and non-countable sets. Countable, uncountable. So here, okay, you have a rather very, let's say, self-contained material on both Moodle platform and Microsoft Teams about infinite sets. And so we shall focus mainly on what countable and uncountable mean. But first of all, we must make a distinction between infinite sets and finite sets on the other hand. So here you must know the definition of an infinite set. So A is infinite, the set A is infinite if there is another set B which is strictly included in A. So they are not equal. Let's write like this. Not equal, strictly included, such that A and B are equipotent. What equipotent means, this is the symbol for equipotency. Equipotent means there is a bijection between A and B. If you remember in our previous lesson, we discussed about bijective functions, surjective and injective. But actually, A is equipotent with B if and only if there is a map F from A to B. Also, we may call it one-to-one. One-to-one means injective and surjective. So a good image for this is the following. This is a one-to-one map, yes? I mean, to every element in A, there corresponds one unique element in B, and to two different elements there correspond different elements. For instance, if to this one we give this one, this is no more injective, as you remember. So this is forbidden in a one-to-one map. And also, the image of the function must be exactly the entire set B. This is a one-to-one map. Okay, remember the example with the students and with the chairs. Yes, if you want to know that in a classroom there are the number of students equals the number of chairs, associate to every student the chair on which it is sitting. And if there are no standing students and no free chairs, there are exactly as many students as chairs. This is a one-to-one map or a bijective map. Another term is bijective. Okay, so a good example for an infinite, otherwise the set is finite. For example, if we take the set of natural numbers, which is defined as follows. According to this definition, it is infinite simply because we have the following proof. This is the proof that the set, one of many proofs that the set of natural numbers is infinite. Yes. In this picture, we see a one-to-one map from the set N to another set, let's call it X, capital X, which contains all the natural numbers but 0. So obviously X is strictly included in N. However, they are in a one-to-one correspondence. The correspondence is this one. Yes, and as you can see, this is a bijective map. This is maybe the simplest proof that, and the simplest example of an infinite set. Of course, there are many other proofs that the set of natural numbers is infinite. Here you are another one. Yes. Here we have the set of all natural numbers, and here we have the set, let's call it Y, the set of even numbers. So there are as many even numbers as natural numbers, because this is a one-to-one map. If you want a formula, here the formula is given by f of n equals n plus 1. And here the formula is f of n equals 2 times n. But the formula is not important. The picture, I think is illustrating better the idea. Yes, here and here. Okay, this is the one-to-one correspondence we talked about earlier. Okay, so we have examples of infinite sets. Another infinite set is the set of integers. And the question is if it is equipotent with a set of natural numbers. So the set of integer is written usually like this. And so on. The set of integers is equipotent with a set of natural numbers, and I let you to write this. The idea is the same as here for with a set of even numbers. Also, at the lecture, we also proved that the set of rational numbers, the set of all expressions of this form, yes, is also equipotent with n. So there is a bijective map from Q to N, and we did that in the lecture. I don't want to enter into many details. You have all these things written, but just to remember. So now we have the following natural question. Maybe in the world of infinite sets, all the sets are equipotent with n, so they have the same number of elements as the set of natural numbers. Well, the answer is negative. We shall see a set which is an equipotent set with, an infinite set which is not equipotent with n. But first of all, the definition, because you asked me about countable and uncountable set. So definition, a set X is countable if and only if it is equipotent with the set of natural numbers. So as we said above, examples of countable sets: the set of natural numbers, of course, the set of integers, the set of rational numbers are all countable sets because they are in a one-to-one correspondence with a set of natural numbers. Of course, there are also subsets in the set of natural numbers which are countable. For example, the set of all even numbers, the set of even numbers, the set of odd numbers are all countable. Actually, attention, what I'm telling now, it's important. Every infinite subset of the set of natural numbers is countable. So countable sets are, in the world of infinite sets, those sets with the least number of elements. Yes, so countable set. Actually, what a countable set means at another level. A set is countable if you can write its elements as a sequence. So X is countable. We made this simple observation, but useful. If and only if you can write X as X1, X2, X3, and so on. And here, if you can write the elements of a sequence, of a set as a sequence, of course, this is the one-to-one correspondence with a set 1, 2, 3, and so on, which is a countable set. So again, a set is countable if and only if we can write its elements, all its elements, as a sequence. You are the first element, you are the second, you are the third, and so on. And in this sequence, nobody's missing. Yes, so, okay, all the previous examples of infinite sets were countable, and this is how actually we prove that they are countable, by writing them like this. And below, you can associate the corresponding natural numbers, and the proof is over. If there is something unclear until now, and now I shall give the definition of an uncountable set. But before that, for example, what do you think about the following set? Is it countable or not? Or this one? For example, the set X, is it countable or not?
Yes, it is.
Yes, it is.
Of course. Can we prove it? Yes, of course we can prove. Here you are the proof. Yes. Obviously, if you want from the set of natural numbers to this set X, the map is, the bijective map is f of n equals n squared. And this is the bijective map which proves that this is countable. What about y? Is it countable or not? Yes, it is countable because one can associate to the element n plus 1 over m squared plus 1. For example, the rational number m over n. Yes, and this is a bijective map from our set y to the set of rational numbers, which is, as we know, as we must know, it's countable. Yes. So in general, if you have a set which is defined by using elements in this way of integers, rational numbers, that is a countable set, because you, in general, I mean, you can define a function which is a one-to-one correspondence from that set to a set about we know that it is countable. So it's important to know examples of typical sets which are countable. And I repeat, these are the set of natural numbers, the set of integers, the set of rational numbers. We must know that these are countable. And then we can make correspondence with another set. If we can make a correspondence, a one-to-one correspondence with one of these sets, yes, it will be countable too. Now, uncountable, now the definition. A set is called uncountable yes, if it has the following two properties. It is infinite, so it satisfies the definition to be infinite. And the second, it is not in a one-to-one correspondence with the set of natural numbers or to any other, so it is not. Or to any other countable set. Now, of course, the natural questions is, are there any uncountable sets, or maybe all the sets are infinite sets are countable? They are in a one-to-one correspondence with the set of, and the answer is yes, there are uncountable sets. And I gave you two examples in two different lectures. I gave you two examples. The first example of an uncountable set is the following. The set of all sequences or strings, you may call them in English, also sequences or strings, of 0 and 1. Now, 0 and 1 are not important. They are not necessarily, don't think to 0 and 1 as numbers here. Think to them symbols. Yes. Take two symbols, 0 and 1, point and comma, for example. That doesn't matter. Two symbols, and take all the sequences, all the strings, all the, yes, of 0 and 1. Now, there is a nice proof that this is not a countable set. It is called Cantor's diagonal argument, and now you have it in the lecture. Tell me if you want to repeat the proof, or you can take it from there.
Can you repeat the proof, please?
Okay, I will repeat it immediately. Okay. So now the proof is important somehow. This was the first example of an uncountable set. It was obtained by the German mathematician Georg Cantor in about 1870. Okay, so of course we shall suppose by contradiction that X is, if X is countable, then it means that we can write its elements as a sequence. You are the first element, you are the second, you are the third, and so on. And here we have all the elements of X. Yes, all the elements of X. So X1, it's an element of X. It means it is a sequence of 0 and 1. I shall write in this way. I shall put here below the index. It means we are talking about X1, and above I shall put the index which shows us the position. For instance, A1, 2, it means it is the second symbol in X1, and so on. X2, similarly, is A21, A22, A23, and so on. X3. And so on, and so on. For example, what do we mean by A32? We mean that this is a symbol in X3 because of this 3. And what position in X3 has this symbol? It has the second position. Yes. So all these elements, A, I, J, are nothing but 0 or 1, of course. Yes. And now we need a contradiction. We need something to contradict our hypothesis that we can write all this set as a sequence. Well, to do that, we need to define an element B, which must be in X and must be different from any X K or any K, equals 1, 2, and so on. So it is in X, but it cannot be X1, it cannot be X2. None of the elements written here, X1, X2, and so on, can be this element which we shall define now. And the definition of B is as follows. So let B, now B1, B2, B3, and so on. Of course, Bj here must be 0 or 1. How to choose B1? And here you have Cantor's diagonal argument. B1, we take it to be different from A11. Now the question, is it possible? Yes, it is, because A11 can be 0 or 1. If it is 0, we take B1 to be 1. If A11 is 1, we take B1 0. So this choice is possible. That's why we need two symbols. How to choose B2? We choose it to be different from A22. Now, same argument, it can be done. So actually, follow here the diagonal of this table. This is diagonals, Cantor's diagonal argument. B3 will be different from A33. The choice is possible, and so on. With these choices, the element B It's obviously an element in capital X because it is a sequence of 0 and 1, but it cannot be x1 because it is different from x1 on the first position. It's different from x2 because it is different from x2 on the second position. It cannot be x3 because it is different from x3 on the third position, and so on, and so on. So this is the proof that this set is not countable, it is uncountable. So it is maybe the simplest example of an uncountable set. Of course, you must recognize simply variations of this example. If I give you, for instance, let the set Y to be the set of all strings, A1, A2, A3, and so on, with AG belongs to, for instance, I don't know, the symbols alpha, beta, and gamma. Obviously, with the same argument, this is an uncountable set, and so on. Yes. In a later lecture, this was in the second lecture, something like that. In a later lecture, I proved that the set of real numbers, it's uncountable with another argument. There you have, I don't make it now, but you find it in the course, in the lecture. I proved there that the interval 0, 1 is not countable. If you want, I can make it now, but also you find it, you can find it on in the lecture and on the lessons I put on Microsoft Teams and Moodle platform. Okay, if there are any other questions about countable and uncountable set.
So if you get for the partial, an exercise like this, it's only things you need to write?
For example, here you are an exercise which could be at a partial, this one. Prove that this set is not countable, it's uncountable. Yes, you must follow exactly Cantor's diagonal argument. But this time, okay, instead of 2 symbols, you have 3 symbols, which is very well. Nothing changed, actually. I give you an example. So you must know, first of all, the definitions, what it means an infinite set, what it means countable, what it means uncountable, to recognize a countable set. Somehow you can make a one-to-one correspondence with a countable set. And the usual countable set, I told, it's the set of natural numbers, integers, and rational numbers, about which we must know that they are countable. And also you must know Cantor's diagonal argument in order to prove with the same idea that other sets which are very close to this one, to Cantor's example, that they are uncountable. For example, something like that. Okay, other questions, please. Or I can continue. Now we have series of numbers. Yes, this was the next topic. Here you must know the definitions, the basic examples, which is the geometric series and the Riemann series, and the basic test of convergence, yes, such as the comparison with n at alpha and so on. For example, if we take the series here, the number p, it's a real number. So the question is to decide, according to the number p, the nature of this series. Is it convergent or divergent? Yes, so p, it's a parameter. In terms of p, we must decide. Maybe the answer will depend on p. I mean, we expect an answer of the following type. For some specific values of P, the series is convergent. For other values, it is divergent. This is more or less what we expect when we have an exercise with a parameter. Okay, how to work? Now, we shall use the comparison test at limit with n at alpha. If you have a series like this with positive terms, the limit test, or limit test with n at alpha, says compute this limit and look for an alpha for which this limit must be non-zero and not infinite. If we find such an alpha, the exercise is over, because in that case, our series has the same nature, so they are both convergent or both divergent, with the corresponding Riemann series with that alpha, with the appropriate alpha you found here. This is the limit test. Okay, how to apply it here? We need first a small transformation of the sequence. So in our case, AN, it is this one, of course. So AN, which is given through this formula, can be transformed a little bit by amplifying with a conjugate. I'm thinking to the formula a squared minus b squared equals a minus b times a plus b. So if we have an expression of this type, if we multiply it by a plus b, it gives us a squared minus b squared. So we shall amplify here with the so-called conjugate of this expression, which is square root of n squared plus n plus 1 plus n. And that will give us, below, we have n at p times the expression we just amplified with. And above, we shall get a squared minus b squared, which means n squared plus n plus 1 minus n squared. Here, these two terms vanish. And we finally obtained this expression. And now we shall apply the limit test in this form. So we shall compute limit when n tends to infinity, n at alpha times n plus 1, and below we have n plus p times. And now it's nothing but a problem of degrees. In order to get a non-zero and not infinite limit, the degrees from above and from below must be equal. Must be equal. So we can write like this. Who is the maximum power above? Above it is n at alpha plus 1. If you take it in front, you'll get 1 plus 1 over n at alpha. And below, there will be n at p plus 1, because you will have here something like that. Yes. And now, of course, alpha plus 1 must be equal to p plus 1. So alpha equals p. So when do we have a non-zero and not infinite limit? When alpha equals p. So our series will be convergent if and only if alpha is strictly greater than 1, says the Riemann series, which means for us p greater than 1. And this is the result. So our series is convergent if and only if the parameter p is strictly greater than 1. If there is any question here, I can make another example if you want, similar
Can
to
you
this
explain
one.
how we did the degree thing?
Please repeat.
The one we got the degrees. Can you explain it again, please?
How we computed the degrees?
Yeah.
Well, here, above, if you multiply, you shall get 8 at alpha plus 1 plus n at alpha, yes? Who is the greatest power here? It's alpha plus 1, yes? So if I take it in front, I mean as a common factor, and n at alpha plus 1 will be 1. So this expression can be written like this. Is it clear here?
Yeah.
Below. For I work here inside the parentheses. So the square root. So inside the square root, I take off the greatest power, which is n at 2. Okay? And now square root of n squared is modulo of n, which is n because n is positive. So now in front of it we have n times 1 plus 1 over n plus 1 over n squared plus n. And now we look here. The first term has the power n at 1. Yes. The second term has the same by chance. It's by chance, just the same power n. So we take off the common factor, which is n. 1 plus 1 over n plus 1 over n squared plus 1. This is it. That's why we have here this expression. And also we multiply now this n with n at p. It gives you n at p plus 1.
Mm-hmm. I got it. Thanks.
Okay. If you want a similar example, I can give you another example. The same idea, for example, let's take now one without a parameter. N at 2 plus 1, and below let's take it n at 3 plus 1 times square root of n squared plus 1 minus n. Again, the same idea. First, we amplify with the conjugate of this expression, yes, which is square root of n squared plus 1 plus n. And after we amplify, we get let's put here n at 4 to be more interesting. And below we get n at 4 plus 1 times what? N squared plus 1 minus n squared. So that will be the sum. So this is our series. I shall write just the sequence an. It will be n squared plus 1 times the parentheses, and here below we have n at 4 plus 1, and this is 1 here. Okay, so this is the sequence. We shall apply now the limit test. So we compute limit when n tends to infinite of n at alpha times this one. Okay, so now the same story with the degrees. Now clearly below the maximum power is n at 4. Above we have n at alpha, okay, times. From this parenthesis we take off n squared times 1 plus 1 over n squared. And from the second parenthesis, as before, first of all, under the square root, we take off n squared, which is the maximum power inside the square. And then we get off from the square n, simply n. And then we have the common factor n times. Yes, it is a similar computation as before. And now we have Above we have n at alpha plus 3. Sorry, yes, n at alpha plus 3 times 1 plus 1 over n squared times, yes, and below we have this. And now this limit will be non-zero and not infinite. It will be actually 1, but this is not important. Important is not to be 0 and not to, if and only if the power from above, which is alpha plus 3, equals the power from below, which is 4. So it gives us n equals 1. So our series has the same nature as the Riemann series with alpha. Sorry, here alpha is not n. Yes, alpha equals 1. For alpha equals 1. So that means with a series sum of 1 over n, which is, according to the Riemann series, this is a divergent. Actually, this is the harmonic series. It's divergent. We must know that this is divergent. So our series is divergent. It has the same nature as the Riemann series with alpha equals 1. So a small variation here, a small change of the initial value for the by amplification with a conjugate, if necessary. Not always it is necessary, but if necessary, we can amplify with a conjugate. And in general, if you have roots and subtractions, like in the previous examples. Okay, other test for series.
I have a question.
Yes, please.
So for this last example, we cannot use the ratio test, for example.
You can use, but it will give you 1.
Yeah, and after we get to Rab-Duhamel, it's
Yes,
a lot of computation. No?
I understand it is much more complicated. Now,
Yes.
ratio test followed by Rab-Duhamel test. It's good to be applied when the expression of the sequence here, it's good for simplifications. It can be simplified rather simple. You understand? Which is not the case here. You have here different products, factorials, powers, exponential, which can be very simplified. Yes? For example, I gave you some examples in the previous lecture. For example, let's take this one. So the sequence AN, it is this one. Obviously, in my opinion, here, the ratio test can be useful. Maybe it will give us 1, which is, it means it will not decide. But anyway, applying here limit test, and we hope that it will decide the nature of the series, it's obviously appropriate because the expression of the sequence AN can be simplified in a simpler way. So this is the sign to use ratio test. Let's use it. Let's apply it. Okay, this is ratio test. Yes, the theory says compute this limit. If this limit will be strictly greater than 1, our series will be convergent. Divergent. If the limit will be less than 1, it will be convergent. And if the limit will be 1, the test doesn't decide. We must go to a stronger test, which usually, you were right when you said, it's a Rabe-Duhamel test. Let's see here. Obviously, we can simplify like this. Before 2n plus 1, we have here 2n minus 1. So this will be simplified by this one. Again, here we have this one and this one, because before 2n plus 2, it is 2n. So the result of these simplifications, finally, it is the following. And also 2n plus 1 with 2n plus 1 from here. Yes? No. This one goes, sorry, this is not a simplification. This will go above. So we have, above we have 2n plus 1 squared. And below we have 2n plus 2 times 2n plus 3. And now this limit is 1. Yes, because the powers are equal. They are quadratic functions. And so the limit will be the coefficient. No, here you have something like this. 4n squared plus 4n plus 1. And below you'll have 4n squared and so on. Doesn't matter the other terms. So the limit will be 4 over 4, which is 1. So this is ratio test. It was an appropriate test for this series when we look to the form of an, but unfortunately the limit was 1. But the try is appropriate. It's normal to use ratio tests here. Now, because it didn't decide, we go further to Rabe-Duhamel test. Rabe-Duhamel test, or simply Rabe, says the following. Compute the following limit. If this limit is less than 1, it will be convergent. It will be divergent. It is opposite to, if it is greater than 1, it is convergent. If it equals 1, actually the test doesn't decide. Don't forget the expression an plus 1 over n, so the reverse of this one, was computed here. So we can take it from here. So when you apply Rabe-Duhamel test, some computations were already done. N times an over n plus 1, it is 2n plus 2 times 2n plus 3 over 2n plus 1 squared minus 1. And now we must compute this limit, which is usually a simple one, not very complicated. At least in this case, it is very simple. N times, make the computations, 4n squared, 6n, so it is plus 10n, plus 6, minus 4n squared, minus 4n minus 1, over 2n plus 1 squared. Now, 4n squared with 4n squared vanish. So it gives us limit when it tends to infinity of, here we have 6n squared. 6n squared plus 5n. Yes? And below we have 4n squared plus 4n plus 1. This limit is 6 over 4, which means 3 over 2, which is greater than 1. So our series will be convergent. But again, the application of the ratio test, even it didn't decide, was natural, and it's good to start with. Because in most cases, the ratio test decides. Here I took an example to see also Rabe-Duhamel test, but in most cases, I repeat, it decides. Okay. This is about series of numbers. Now the next will be power series. Yes, power series. Elementary functions, Taylor polynomials of the first and on the second degree. Yes, for functions of one single variable. Okay, if what to start? What do you want to start with? Here you must know how to compute the radius of convergence of a power series, and so on. Okay. Let's see, for example, let's consider the following power series. Let's put it with 2. Let's consider this power series. Yes. The question, compute the radius of convergence, then compute the domain of convergence, and compute the sum. From the very beginning, it must be said that the sum can be computed by reducing somehow our series to the geometric series, which is this one. We must know the geometric series when it does converge, when the ratio is strictly less than 1 in module, and the sum it is this one. After the break, we shall solve this exercise, but the geometric series is the main argument here. Okay, so we take a break.